Hi, it's Dr. Khan with sections 5.5 to 5.8, Earthquakes in the Earth's Interior. Here are the learning objectives for this section. We're going to first take a look at the destruction that's caused by earthquakes. And the same size earthquake can cause different levels of structural damage to the built environment or the human built environment based on a couple of factors. So first of all, obviously the intensity of the earthquake is going to matter, whether it's a 4 or a 7 on the Richter scale. We already saw makes a big difference. But then also the length of time that the shaking takes place, that duration of the vibrations. And then what is the building built on? Is it loose sediment underneath it? Is it glacial rubble like we have here in our area? Or is it bedrock that the building is built on? And it ends up that really matters, that some ground material can actually work to amplify or increase the wave shaking that's going on the ground. And then also the design of the structure itself, including the materials used to make the building. So destruction results from shaking of the ground, and again, that ground material can serve to amplify or heighten the amount, the wave heights in order to increase the shaking. But another concern is what's called liquefaction of the ground. So if we have ground that's a wet, saturated material, the shaking can actually make solid ground turn into a fluid-like substance. So at least it's acting like a fluid. So what we can find in that situation is that underground objects might actually float up to the surface. Things that are buried underground or people that are buried underground could float to the surface. And then also the surface can act kind of like a quicksand where whole buildings can sink into the ground as well. We see this here with an earthquake that occurred in 1964 in Japan, and you can see the buildings are toppled over or somewhat sunken into the ground. Also, we get destruction from landslides that occur as a result of earthquakes and what's called ground subsidence. That's just fancy for sinking of the ground. Fires that are caused, and tsunami, which are waves that are generated when the ocean floor is displaced. I do recommend that you take a minute to look at the next smart figures. There's 2 of them, so I would pause this video and take a look at them. It does a very good job of describing landslides, and the next one talks about what's actually happening when a tsunami is generated when we displace that land. And I really want you to pay close attention to this area here, this bulge that's being caused as this subducting plate is coming underneath the overriding continent. So we have this plate moving down here, kind of, bending really the plate where these are meeting. So there's a lot of stress that's building up here. And as soon as there's slippage along that fault, this land area is going to return back to its shape. We see that happened here. Here's the original bulge, but it went doing back into place. And as a result of that doing, this area here was uplifted, and it's going to uplift the water in the same fashion. So the water is going to have a wave that's generated through and traveling very quickly towards the surface. As those waves approach shallower water, they stand up taller and taller compared to the surface here and inundate the coast. Section 5.6 talks about where most of our earthquakes occur, and most of them come from a very small set of areas on Earth. So it's saying here 95% of energy from earthquakes just occur in a few narrow zones. So we have an area around, that's what circum means, around the Pacific, and also the Alpine Himalayan belt as well. And we see a visualization of that here. All around the Pacific Ocean, we have subduction zones that end up generating a lot of our earthquakes. And then again, near the Alpine Himalayan belt up here. But notice we also see other patterns within the dots that are represented on this map, places where we'd expect the ground to be moving because there's some kind of plate boundary or magma that's moving. So we have our Mid-Atlantic Ridge where these plates are divergent, they're moving apart from each other. As that magma comes up and the plates move side to side, we expect the ground to be rumbling. really our earthquakes give us a good outline of where most of our major plate boundaries are. We don't really have a great reliable way to devise a short range prediction system. There are sometimes that earthquakes have what are called foreshocks, those that shaking that happens before the main event, or ground elevation might change. So we can monitor that with things like satellites that monitor the elevation of our land. In terms of long range forecasts, though, we can look to the rock record to see what has happened in the past in a given area and look for what are called seismic gaps. So, knowing that earthquakes happen and they happen again and again and again in certain regions, we can assign certain probability statistics to say that, you know what, this particular area of this particular fault really hasn't relieved the stress that's been building up for a very long time, and therefore it's more probable that this particular section of the fault might rupture. So we look for those seismic gaps to see what hasn't relieved stress in a long period of time. One way we look at those prehistoric earthquakes is by looking at our rock record, looking at the different layers of rock that are faulted. So a fault will actually displace one rock unit from another rock unit, and we're seeing that here. This is the before, where all of the sedimentary rocks are laid down in layers and everything is parallel to each other and horizontal. But after an earthquake occurs, we sometimes get uplift, and we see here that the rock units are no longer horizontally aligned with each other. And then over time, we have things like erosion and a further progression of the fault here, with more subsequent earthquakes, erosion, etc., to the point where we can actually see these pink lines here representing a layer of sedimentary rock no longer match up, like not even close, right? We have a lot of sediment that's still filled in and erosion that's happened, but we can kind of model then based on those layers, when that fault erupted and when we might expect for that fault to be, quote, ready to rupture again. So again, based on the erosion and sediment, and then erosion and sediment, based on those repetitive processes of earthquake, erosion, sediment buildup, we can reconstruct the story of what happened at a particular location. In order to minimize our earthquake hazards, we need to make sure that we're building buildings that will resist destruction in earthquakes. And we have some really great ways to do that. It's not always something that's cost effective, right? We might have to spend some extra money or select better materials in order to make sure that our buildings are going to withstand an earthquake. We do have some early types of warning systems that measure P waves. If you remember, P waves are the primary waves. Those travel the fastest and they arrive before the surface waves will arrive. And remember, the surface waves are the ones that are the waves that are destroying structures on the ground. So the P waves will arrive first at a given location. So this actually the system is intended to detect those P waves and then shut down infrastructure in Japan in order to protect it. The Earth's interior is really mapped out based on the evidence that we've collected from earthquake events. We don't have a way to look inside of the Earth. We've only drilled through a small fraction of the crust. But waves that can travel through the Earth actually end up providing a lot of information about what's going on down there. If we look at how long it takes P waves or S waves to travel through the Earth, well, depending on the density and properties of the material in the different layers of the Earth, P wave and S wave might speed up or slow down. We also know that S waves only travel through solids, so they're not going to be moving through a liquid. So based on those two pieces of information and the knowledge of how P waves and S waves either speed up or slow down based on the density of the rock that they're traveling through, we can actually map out what the interior of the Earth looks like. And that's actually how we figured out that part of Earth's core is actually a liquid. because our S waves would not travel through them. We see the bending or diffracted waves, the bending of the waves around this area here, so they're not traveling through, they're diffracted. We see a reflection of waves, in some case a double reflection of waves. Waves that will travel through the earth still change speed and direction based on the density of the materials underneath. So again, based on this information, we're able to create this model of what the interior of the earth looks like. So we know we have the crust, that's the thin, rocky outer layer. Continental crust is granitic in nature, and it's less dense than ocean crust. We have some crust that's up to 4 billion years old. So we have some rock record that goes through most of Earth's history. The oceanic crust is basaltic in composition, and it's more dense. It's also a lot younger. The mantle comes next, and it is below the crust. It's the biggest layer in terms of volume. The outer core, we noticed that the S waves didn't pass through, meaning we suspect that that is a liquid outer core. It's composed of iron nickel, and it's very dense. A lot of overlying planet, right, is kind of weighing everything down, and it's made up of dense materials to begin with. Iron and nickel are materials that are denser than our rocky materials to begin with. And the inner core behaves like a solid because it has to. There's extreme pressure